Hi, I'm Nick Letherby, the IoT Ecosystem Manager at TI. I'm presenting a 5-part training series titled Understanding Secure Connectivity in IoT Devices that looks at security technologies commonly used in IoT devices and embedded systems. I'm going to start with the first module, which is entitled Understanding Security Threats to IoT Devices, which looks at what hackers are trying to achieve, how they go about attacking embedded systems, and gives several real-world examples of attacks on embedded systems that should help you understand why some of these security technologies are needed and what threats you need to counter when developing an IoT device or embedded system. To appreciate the security countermeasures your product might need, it's good to start by understanding what attackers might be trying to achieve. You're doubtless familiar with hacking exploits such as credit card data theft or identity theft, and probably also with bot attacks where embedded systems or personal computers are taken over by malware to mount denial of service attacks on targeted websites. However, hackers can do a lot of different things beyond this. One aspect to consider is protection of your product's intellectual property. For example, an attacker might be trying to steal your software image so they can clone your product. Or they may be trying to steal an advanced motor control algorithm to take away a competitive advantage you may have. You're probably familiar from the last US election about how hackers leaked information to damage some of the candidates involved in that election. And another aspect to consider is ransomware, where a hacker may get malware into the system where they can encrypt a company's data and then force the company to pay them money for it to be decrypted. And then finally, there's examples of electronic warfare where actual equipment has been damaged or disabled through remote attacks. While hackers will certainly have a number of different motivations for trying to break into your system, they generally are going to do it via 3 ways. They're going to want to try and compromise your identities or keys, security keys used to access the system. And once they're in the system, they want to either read data to discover information, read code to maybe steal your software image, or they want to modify code or data to start taking over your system. So we call these 3 main objectives, which are security credentials, data, and code, assets. So how do attackers get access to your assets? There's 3 places where they may be exposed. For example, if you have your software image out in external flash, it could be read out of that flash chip. Another time things are exposed is during transfers, and these can be both remote transfers over a network or even transfers on a board between, for example, a memory chip and the actual main CPU. And then finally, there is runtime. Inside the chip's memory, assets may be exposed there that were encrypted possibly somewhere else, but once they get into the chip's memory, they need to be decrypted so it can work on them, and that gives another chance for attackers to access them. These 3 particular areas, access points, can be attacked in really 2 primary manners. The first is a physical attack. Typically, this will only be done by the most dedicated, well-resourced attackers. They will actually get actual product, and then they can use bus analyzers, logic analyzers to look at any traffic coming in and out of the device, or even traversing the PCB board. If you have debug ports or JTAG ports that you intend your service personnel to use for diagnostics, an attacker may be able to use those to actually see how the actual device is functioning at runtime. And then finally, they can, for example, remove the flash device from your board, plug it into another board, and read out the contents to get your software image, for example. More commonly, attacks will be done remotely. To get information that's being transferred across a network, there are a number of attacks possible, such as packet sniffing or something called a man-in-the-middle attack, which we'll discuss in a little bit more detail in a couple of slides' time. If the attacker wants to actually control your device and get the data exposed at runtime or in storage, they need to download some malware. And once they have malware running on your device, then they can do all kinds of operations, such as reading and writing memory. We just discussed how remote attacks are much commoner than physical attacks. Here I just want to go over a couple of common remote attack techniques. One thing that's significant about both these techniques is they're designed to get around the fact that the target is actually using encryption. And they'll show you that just encrypting messages is not sufficient in its own. Let's look at the man-in-the-middle attack. In a man-in-the-middle attack, a client will contact the server with the intention to establish an encrypted communications channel. The attacker will attempt to fool the client that it is in fact the server, so the client then establishes its encrypted channel with the attacker's server, and then similarly the attacker's server then poses as the client to the actual real server and establishes an encrypted channel with that server. At that point, the attacker knows the encryption keys for both the server connection and the client connection, and it can simply monitor and decrypt all the communications between them and insert any of its own messages if it wants to cause confusion and problems. So you can see the problem here is that while the client did set up an encrypted channel, it didn't bother to check who it was setting up with. And so one concept we'll be discussing more later is authentication, where you make sure that the person you are contacting really is the person you want to contact. Another form of attack is the replay attack. Let's imagine a situation where a client is connecting to a server, and the first thing the server does is ask for some login credentials, such as a password. The client encrypts those login credentials, sends it to the server, and is then allowed to connect and access the system. Now these credentials are encrypted, so they can't be read by simply sniffing them. However, if you do sniff the credentials, it's possible for the attacker to then contact the server at a later time, posing as the client. And when the server asks for the credentials, it simply sends the credentials packet it sniffed earlier. The server allows it to connect, and at that point the attacker has access to the system. So the issue in this instance was that an attacker was able to take a packet used in an earlier session and then create a completely different session with the server and still use that same packet successfully. To counter this, the credentials packet should be encrypted to include some form of sequence or session number, and that way the server can tell if the packet is really associated with the existing session it just started, or in fact was captured from an earlier session and therefore likely to be part of a replay attack. Having gone through a number of the ways that attackers will try to break into systems, let's look at a few examples of real attacks that occurred. One apparently repeated attack was on a number of large retailers where credit card details were stolen. Target, Home Depot, and Sally Beauty were just some of the retailers targeted by this attack. The attackers used a third-party vendor login to gain access to the main company network. This only had limited access, this login capability, but then they were able to use Windows vulnerability to penetrate the main corporate network. Once they'd penetrated the network, They scanned the network to identify all the point of sale terminals used by the company. And they also scanned the network to look for Visual Basic scripts made by network administrators, and found that these network administrator scripts usually contained admin passwords and logins. Once they had the ability to get admin rights, they were simply able to then install malware on all the point of sale terminals, and the malware just sat in the memory and then captured credit card details as they were exposed in the main memory of the CPU, and then they sent this data to the attacker's server. Now, since these large companies typically have monitoring software to detect hacking attempts, they encrypted the credit card details to make sure they weren't obviously credit card data, and they disguised the data as DNS traffic, since there's a lot of DNS traffic on the network, and that way they're able to avoid any issues with monitoring software detecting them. In the previous slide, we discussed one common embedded systems application, a point-of-sale terminal, and how that had been compromised. Let's look at another very common embedded systems application, a smart meter. In this attack, the attack was carried out using physical access. Smart meters deployed in Puerto Rico had an infrared diagnostics port, but there was no security on that port. Unscrupulous technicians working for the company were able to take their own PCs, add an optical converter, and then connect into that IR diagnostic port. Then, using some software available over the internet, they could install it and alter the parameters for meter usage reading. What that meant is that a meter would then report much less electricity use than was actually occurring. The rogue employees would then make a charge to the customer for their service. It was estimated by the FBI that the company lost perhaps as much as $400 million a year, and that up to 10% of meters have been hacked. One of the key problems here, other than, of course, corrupt employees, is that the diagnostic port lacked any type of security credential. So there was no way to stop people from accessing if they had appropriate infrared connectivity on their PC. And there was no way to find out who had accessed it. In addition, the security key for the device was not an encrypted memory, and it meant once the device was accessed and some malware had been downloaded, it was possible to get hold of the security key and modify program parameters, since you could break the encryption on them. So again, two obvious weaknesses here: an unprotected diagnostic port and an unprotected security key. Another very common embedded application is the programmable logic controller, which is used in lots of industrial control and automation type applications. Stuxnet was a virus that was believed to be developed by the American Israeli intelligence organizations to prevent Iran from enriching uranium. Since the facility that contained the uranium enrichment equipment was actually disconnected from the internet, there was no way to remotely attack it. Therefore, Stuxnet was designed to be extremely infectious, but only activate in very specific conditions. It is speculated that the initial infection took place via USB sticks being taken into the facility. Then once on the internal network, it used previously unknown Windows vulnerability to spread across and access the various programmable logic controllers that controlled the uranium centrifuges. These programmable logic controllers, these PLCs, all had default passwords that could not easily be changed. Stuxnet took advantage of this to modify the behavior and spin the centrifuges at speeds designed to damage them. In addition, it modified the PLC software to report fake data, which implied to people monitoring the centrifuges that they were actually working quite normally. Because it was so infectious, Stuxnet spread to many, many machines across the internet. To avoid it being detected, the developers had Stuxnet look for the specific programmable logic controller software and then check the geographic location before activating the virus or activating the behavior. And this way it only actually causes any damage at the specific location. The fourth example of an attack technique is Heartbleed, which is a well-publicized open SSL or TLS bug. TLS or SSL is the standard internet security protocol. Heartbleed was actually found independently by a couple of different cybersecurity research people. It's not absolutely certain it was ever used because an attack via Heartbleed leaves no trace of actually having occurred. However, a number of organizations believed that the attack was exploited immediately after it was published and before they deployed a patch. And it's also quite likely that intelligence organizations had discovered it sometime earlier and used it to perform attacks. Heartbleed differs from some of the other attacks we talk about in that it uses a insecure software API to extract information. The way TLS works is that it can send a heartbeat message, and so the client will send to the server a heartbeat value, and the job of the server is to return that heartbeat value to confirm that yes, it's still alive and the connection is still valid. The flaw in the API was that it did not check whether the amount of memory requested to return the heartbeat value actually matched the amount required to contain the heartbeat. So an attack would function as follows. A client would send a heartbeat request, and they would send as a heartbeat value, say, for example, a 16-byte value. They would then request that the API return 64 kbytes of memory to include the heartbeat value. This essentially enabled the attacker to get 64 kilobytes of memory back from the server, which could then be analyzed for security keys, usernames, passwords, and other critical security credentials. In addition to allowing up to 64 kbytes with one request, an attacker could make multiple requests of 64K, thus getting access to large amounts of memory on the server associated with the TLS or SSL program. So let's summarize some of the security vulnerabilities we've noticed in these examples. A pretty common thread is poor password security, with either being default passwords for a product that couldn't be changed easily, or passwords left in admin scripts, and then a lack of password security by partner employees. And in general, passwords are often prone to problems because humans are the ones managing them. The second theme that came up was the fact that security credentials were available in unprotected storage or somehow accessible at runtime. If we go back to the smart meter, the security key there was not protected, it was in open memory. And if we go back to the Heartbleed example, a whole series of security keys and passwords and usernames could be accessed because those credentials were not protected from the Heartbleed API grabbing memory that contained them. Physical access is a potential issue. If you have an unsecured debug or diagnostics board, it can be exploited. And as we saw in the Heartbleed example, poorly designed APIs can enable hackers to get access to memory they shouldn't be able to read in normal cases. Though we didn't give an explicit example here, poorly designed APIs can also be used by hackers to insert malware and get that running on a device as well. So paying attention to APIs, and especially how memory is managed, is very important. Hopefully you now realize that the security challenge for a connected or IoT device is multifaceted. It's up to you, the device manufacturer, to identify the threats that are relevant to your products. For example, a consumer wearable will not need the same level of security that, say, a military communications equipment would need. We discussed several examples of actual attacks on embedded devices and highlighted the security vulnerabilities that led to them. These are clearly things you need to avoid in your design. The next module in the series is Core Cybersecurity Concepts and their relationship to microcontroller security hardware. In this module, we'll discuss the key security concepts such as authenticity, integrity, and confidentiality, and how these can actually be enforced by the security hardware and firmware found on today's microcontrollers. At some point, it's likely you'll want to do some actual software development of a secure connected application. I've put a few links here to enable you to get the appropriate software and evaluation modules to develop secure connected applications on a TI SimpleLink Wi-Fi device. We have an extensive set of hands-on training modules called SimpleLink Academy, and if you go there and select, you'll see a number of examples that deal with secure connectivity, secure storage, and cryptography.